Theory we'll be using today is that when two objects come in contact with each other, the hotter object will lose thermal energy and the cooler object will gain thermal energy. So the formula that we'll be using today, based on our theory, the loss in heat energy is equal to the gain in heat energy, and that can be expressed mathematically as m1 times c1 times the quantity θ1 minus θf is equal to m2 times c2 times the quantity θf minus θ2, where m1, c1 and θ1 are the mass, specific heat capacity and initial temperature of the hot object. m2, c2, θ2 are the mass, specific capacity and initial temperature of the cooler object, and θf is the final temperature of the mixture. So let's get into an example. Unfortunately, there is no electricity and Zakia wants to take a bath. She boils 1.5 kilograms of water and pours it into a bucket holding 4.5 kilograms of water at 30 degrees Celsius. What will be the final temperature of the mixture? Assume that the water is pure and is at sea level. Our solution? We start off by listing our givens. So the mass of the hot water is 1.5 kilograms. Since it is water, its specific heat capacity is 4,200 joules per kilogram degrees Celsius. The initial temperature of the hot water, since it is boiling at sea level, would be 100 degrees Celsius. M2, the mass of the cooler water, is 4.5 kilograms. Since it is water also, it would be 4,200 joules per kilogram degrees Celsius for its specific heat capacity. And the initial temperature of the cool water is 30 degrees Celsius as stated in the problem. The final temperature is what we're to find. Next, after identifying our givens, we proceed by writing our formula. Then we substitute our values. After we substitute the values accordingly, we would simplify by multiplying 1.5 times 4,200, which would give you 6,300. And then 4.5 times 4,200 gives you 18,900. Next, we expand brackets. So 6,300 times 100 gives you 630,000. And then minus 6,300 θf equal 18,900 θf minus 567,000. Transposing, we'll have 630,000 plus 567,000 equal 18,900 θf plus 6,300 θf. Adding, we get 1,197,000 is equal to 25,200 θf. So θf would be 1,197,000 divided by 25,200, which would give you 47.5 degrees Celsius. So it would be a nice warm temperature of 47.5 degrees Celsius that Zakia is used to when bathing with the electric heater. Another way we could have worked out this problem is by not using 4,200 joules per kilogram degrees Celsius for the specific capacity of water. Although we know it, we don't have to use that value because since it is water being mixed with water, the specific heat capacities would be the same. So instead of that value, that number of 4,200, we could use any symbol for it. So in this case, I have chosen to use the symbol C. C for the specific capacity of the hot water and C for the specific capacity of the cold water. So our formula would remain the same, and now when we substitute, it would be 1.5 times C times all the rest and so on and so forth. And since it is the same C on both sides of the equation, what would happen here is that they would cancel out. You can divide both sides by C since it is the same. So then you would be left with much smaller numbers, only 1.5 times in brackets 100 minus θf, and on the other side 4.5 times in brackets θf minus 30. So expanding brackets, 1.5 times 100 is 150, and we'll have minus 1.5 θf and 4.5 θf, and on the other side 4.5 times 30 is minus 135. And then we transpose and add 150 plus 135, add 4.5 plus 1.5, we get 285 is equal to 6 θf, so θf would be 285 divided by 6, which would give you the same answer of 47.5 degrees Celsius. The advantage of doing this method is that if you don't have your calculator, you can still get the answer without having to do with big answers. And if you don't know, let's say maybe the specific capacity of the substances, as long as they are the same, you don't need to know what the specific capacities are. Or maybe let's say the masses. As long as you know how much mass is in one and how much mass is in the other, if you don't know the exact values in terms of kilograms or grams or liters or anything like that, you don't need to know it as long as you have a relationship between them. Maybe, for example, let's say if one is twice as much as the other. So let's get to our practice problem. So pause the video at this point in time, work it out, and then when you're finished, unpause and check the answer in 3, 2, 1. So our first example, 0.1 kilograms of metal is transferred from a furnace at 1092 degrees Celsius to 0.5 kilograms of water at 20 degrees Celsius. The final temperature of the mixture is 42 degrees Celsius. What is the specific heat capacity of the metal? Use that the specific capacity of water is 4,200 joules per kilogram Kelvin. So we start by identifying our givens. We know that the mass of the hot object is 0.1 kilograms. Its initial temperature is 1092 degrees Celsius. Its specific capacity is unknown. For the cooler object, the water, the mass is 0.5 kilograms. Its specific capacity, as usual, is 4,200 joules per kilogram degrees Celsius, and its initial temperature is 20 degrees Celsius. We are also told that the final temperature of the mixture, both objects in contact with each other, is 42 degrees Celsius. So we proceed by writing our equation, and then we substitute our values. So in simplifying, we'll have 1092 minus 42 giving us 1050, and 42 minus 30 giving us 12. Always simplify inside brackets first. Then 0.1 times 1050 is 105, so we have 105C equals to 25,200 when we multiply all those values on the right hand side. So C will be 25,200 divided by 105, which gives us 240 joules per kilogram degrees Celsius. Our next example. Once again, the electricity has gone and people have to get ready for work. How much boiling hot water must be added to 5 kilograms of cold water in a bucket at 10 degrees Celsius for the final temperature to be normal human body temperature? So we start by identifying our givens. This time, the hot object's mass is unknown, but its specific capacity is 4,200 joules per kilogram degrees Celsius. The initial temperature of the hot object will be 100 degrees Celsius, assuming that it is pure water boiling at sea level. The cooler object, the cold water, has a mass of 5 kilograms. Its specific capacity is also 4,200 joules per kilogram degrees Celsius. Its initial temperature is 10 degrees Celsius. And the final temperature, what will the final temperature be? It is not stated explicitly in the problem, but it is stated implicitly. You should know that the normal human body temperature in degrees Celsius is 37 degrees Celsius. So we write down our formula and then we substitute. This time when we substitute, as we notice, there's 4,200 on both sides of the equation, so we can cancel those out. And then simplifying in brackets, 100 minus 37 is 63. And then 37 take away 10 is 27. So we have m times 63, which is 63m, and 5 times 27, which is 135. So m will be 135 divided by 63, which is 2.14 kilograms to the 2 decimal places. So practice on these problems here. Pause this video and continue when you're ready. The answers will be revealed in 3, 2, 1. These are the solutions.